Hello, welcome to a recorded lecture. I'm going to give this a try, see how it goes. It's a little weird because I'm just on my own in a room. So get out your Chapter 7 handout. Make sure you have that handy. This is a review question, just like we start every class period with. So feel free to pause right now and work out this problem. So this is a Chapter 6 problem. So go ahead and pause it and work it out and come back. Okay, so we're using gas laws with density. And remember, we solved for that density equation in class. So the density of a gas is equal to the molar mass times the pressure divided by RT. What density does oxygen have at 35.8 degrees Celsius and 747 torr? So you know you're going to have to convert these to Kelvin and to atmospheres. So what you're going to be doing first here is taking the Celsius temperature, adding 273, and getting 308.95 Kelvin. Then you're going to take your pressure in torr and use your conversion chart to show you that 760 torr for every 1 atmosphere, and it gives you 0.983 atmospheres. Then you're going to plug it into this equation. The molar mass of oxygen is 32 grams per mole because each oxygen is 16 grams per mole, multiplied by the pressure divided by R. Remember, R is always this exact same constant. And then here's our temperature in Kelvin, and we get 1.24 grams per liter. So that is just a review from Chapter 6, which will come up again in a final or whatever ends up happening at the end of the semester here. So I'd like to keep going. We talked a little bit about wavelength and frequency. We talked about the electromagnetic spectrum. That's where we left off with Chapter 7. So again, make sure you have that Chapter 7 handout out in front of you because you are going to be working through it as you follow along. Wavelength and frequency are related by C equals lambda nu. So lambda, this thing right here, is the wavelength in units of meters. Nu is the frequency in hertz, which is the same as inverse seconds, or 1 over seconds. C is the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. So C is always going to be that constant. So now let's practice using wavelength and frequency calculations. So you'll find this on your handout. What is the frequency of a yellow-orange light, which is 589 nanometers, produced by sodium vapor streetlights? So we're given lambda, the wavelength, and we want to solve for the frequency. So feel free to pause it if you want to work on problems. For the sake of the recording, I'm just going straight through, but I highly encourage you to pause it and work on it and then come back to the video. Okay, so we have our wavelength, which is 589 nanometers. And then C, you'll notice this one for C, it has 4 significant figures. So rather than being 3 times 10 to the 8th, it's 2.998. And so you'll see this sometimes, it's the same number. And then we want to know what is nu, or the frequency. So the first thing we need to do, remember our equation here that C equals lambda nu. Then we want to rearrange, divide both sides by lambda. So then we have nu equals C over lambda. Then we need to convert nanometers to meters. So there are 10 to the 9 nanometers for every 1 meter. So then we get 5.89 times 10 to the minus 7 meters. Then you put this into the equation here. So you'll put C on the numerator and lambda on the denominator. And you'll get 5.09 times 10 to the 14 inverse seconds or hertz. So you'll see at the bottom, those units are the same. They're interchangeable. Okay, so now go ahead and pause it and try this one on your own. And I will go ahead and work it out. Pause it first and see if you can figure it out. So a laser used to fuse detached retinas, and this is actually due if you go in for a surgery, if your retina becomes detached, they'll use a laser to do this. produces radiation with a frequency of 4.69 times 10 to the 14th inverse seconds or hertz. What is the wavelength of this radiation? Okay. So again, you're going to start with that same equation. And I like this little rainbow thing because it makes me happy because I'm talking to myself in front of a computer and I feel like a crazy person. So I'm going to use this rainbow thing. If you don't like it, let me know and I'll stop doing it. So C equals lambda nu. Then we want to rearrange. We're trying to solve for wavelength here. So that's this guy. So we're going to divide both sides by nu. And then we have that lambda equals C over nu. Then I think we have the units that we need, so we don't need to convert anything. So then this is 3.00 times 10 to the 8th meters per second. And nu is given in the problem 4.69 times 10 to the 14th inverse seconds. So the seconds here are going to cancel. And then we're going to be left with units of meters, which makes sense for a wavelength that should be in units of meters. So if you put that in your calculator, you should get 6.40 times 10 to the minus 7 meters. And a lot of times you can see that's not a very friendly number maybe, so we'll often convert that to nanometers. And the way you'll do that is you'll say there are 10 to the 9 nanometers per meter. And so this is going to give you 640 nanometers. So especially with the visible region, you know, it's about 400 to 700 nanometers from red to violet. So it'll usually be hundreds of nanometers. So that's usually a good unit for it. All right, so hopefully you got 640 nanometers for that problem. If you didn't, go ahead and pause the video and rework it. Okay, so now you know a little bit about electromagnetic radiation. So why it's important for chemistry and quantum mechanics? So it's because light is a wave and a particle. Particles also exhibit properties of waves. So this is especially significant when particles are really, really small, like electrons. So even big objects have a wavelength associated with them, but we don't notice that because it's so massive. But if you're looking at like an electron, the wavelength is on par with the size of the electron itself. So then it starts acting really weird. And that's where quantum mechanics comes in. Classical mechanics, so if any of you have taken a physics class, it's probably been with classical mechanics, you know, like if I toss this ball in the air, how is it going to move? You know, with a parabola it's going to make, when it's going to fall. That's the physics of large objects, and it does not explain the behavior of atoms and electrons. So we're going to talk just kind of really briefly about the history of quantum mechanics so that you can get just some feel for it, have a little bit of background. It's not going to be thorough by any means, and if you're interested, I highly suggest that you seek out some other resources because I think it's really interesting. So the three things that I'd be familiar with that led to the quantum mechanical model of the atom are black body radiation, the photoelectric effect, and line spectra hydrogen atom. So you can see there's a little bit of a description on these on your handout. So black body radiation, this is a theoretical body that absorbs all frequencies of light. So kind of anything that's black, like it's really just a black body, is going to absorb light. So you guys have probably, you know, heard if you're wearing a white shirt, it's reflecting all light, and if you're wearing a black shirt, it's absorbing. And you probably noticed that too, right? Like if you get hot. So this is, it's kind of, it's not exactly like your shirt, but it's a black body. So classical physics says energy is infinite at high frequency and short wavelength. So the classical physics prediction here, so this is wavelength along here, is radiation intensity. So the classical prediction, just the classical physics, would tell us that energy is just going to go infinite. So if we go to a higher frequency, shorter wavelength, it's just going to go to infinity, which you all probably know is not true, right? But it turns out this prediction gives you kind of what's known as the ultraviolet catastrophe. So the UV region is over here, which is why they name it the ultraviolet catastrophe, because in the UV region, we expect it to keep going up to infinity. But what happens, you can see from these curves, is it actually comes down. So at any temperature, sorry, my little box keeps popping up. At any temperature, it is simply more probable for an object to lose energy by emitting a large number of lower energy quanta than a single very high energy quantum that corresponds to ultraviolet radiation. So rather than losing that full energy at once, it's going to lose little packets of energy instead. And the result is a maximum in the plot of intensity of emitted radiation versus length. So this maximum here. So where here it's going to be lower, come up, go down. So this is the black body radiation. Then we have the photoelectric effect. So this is something that Einstein did. The photoelectric effect is the phenomenon of light striking a metal surface and producing an electric current or flow of electrons. If radiation is below the threshold energy, then no electrons are released. So here's the energy coming in like you're shining light, and this is a metal object down here. And these little guys are the electrons in the metal, and they're being ejected. So if you add the correct energy, then you can eject these electrons. So it was first thought that if you just kept adding light, even if it wasn't high enough energy, that it would absorb it and eventually you could get something to eject. But it turns out that no matter how long you shine that low energy at it, it's never going to get enough to eject the electrons. In your book, it does show you there are some calculations with the photoelectric effect, but I do not expect you to be able to do calculations. I just want you to be aware of this phenomenon. So then the third evidence, or that kind of did classical mechanics and quantum mechanics, was a hydrogen atom, basically, the line spectra. So according to classical mechanics, the electron orbits like a planet and would continually lose energy in the form of light and spiral into the nucleus in a small fraction of a second. Classical physics predicts that no atoms would be stable. So obviously this is wrong because, we're here and all this stuff. So that's a little bit about the hydrogen atom. And then the line spectra thing comes in here. So light emitted by hydrogen contains distinct wavelengths that are specific to hydrogen. So they do have these at the Natural History Museum. I was going to say go check it out, but I'm pretty sure it's closed right now. So there's a hydrogen lamp here. So you're putting actually energy into that. There's hydrogen gas in here, like little hydrogen molecules. And as you add energy to them, they absorb that energy, and that promotes their electrons to a higher energy. Then that goes through the slit and a prism. And hopefully you guys have all played with a prism and shown light through it and see how it splits up and makes a rainbow. So if you're using light from the sun, you'll get the whole rainbow because it has all of the frequencies in there. But if it's just coming from hydrogen, so this is electrons relaxing, and that's letting off those photons or little packets of light. You split it through this prism, and what you find are that you have these distinct lines, and not very many of them. So it's not continuous energy. So if this were white light, if the sun were over here, and we were doing this, we would have the entire rainbow, all different wavelengths of energy, or wavelengths of photons, all different energies. But with hydrogen, we just get these very distinct lines. And so this is called an emission spectrum because it's emitting the light and we're looking at it. And so this was one experiment that said, hey, classical is not explaining this. So we can look at, the one we just looked at was an emission spectrum. So an atomic emission spectrum, a characteristic series of bright lines produced by high temperature atoms. So that high energy hydrogen gas that we were talking about. Then you can also have absorption. So that's just the exact opposite of emission. A characteristic series of dark lines produced when free gaseous atoms are illuminated by a continuous source of radiation. So if it's not emitting it, it'll absorb kind of the exact inverse. So here's an example of emission, and then we'll look at some absorption spectra. So these are atomic emission spectra of some element. So here we have hydrogen, and you can see you just get these very specific lines. Then helium, you get some more, and neon, you get all these other ones. So the reason is we have more and more electrons. So we're going to find out, we'll talk more about that, but it gets more and more complicated when you have more electrons. The electrons just make everything super complicated. All right, so then this is absorption. So you can see this is the exact opposite. So here, let's take a quick look at this hydrogen one, and I'm going to flip back to the previous slide. So you can see you have the entire, sorry, my daughter is screaming at me, so I'm going to go ahead and stop the recording here, and then we'll start again.